Great. So we're on time. My pleasure to welcome Massimiliano Esposito, and I think let's get going. Great. Thank you all for coming.
Okay. Thank you very much for the invitation. So I'm gonna try to give you first a very brief overview of what we're trying to do in the group. So we learned over the recent 20 years how to do stochastic thermodynamics or thermodynamics of small systems. And somehow we want to go back to the large scale and to the complexity of living system computational devices and using stochastic thermodynamics as the basis. And I think there are two big challenges when trying to do that. One is the size of the system increasing, and so the phase space becoming bigger and bigger. And the second one is as the description needs to be coarse-grained for practical purpose, how to keep a thermodynamically consistent coarse-grained description. But today I'm going to focus on the question of large systems. And more specifically, the question will be the following. We know that at equilibrium, the probability distribution of a system is given by the Gibbs, at least for a system in contact with the thermal bath, by the Gibbs or canonical distribution. And the argument in the exponent is the energy or the free energy if there's an internal entropy assigned to the state X. And when the system is large, we have a large deviation principle at work that allows us to argue that the exponent is given by the difference between the intensive free energy minus its minimum. And that's the typical way in which one describes phase transition that emerge in these large scale limits. So the scale parameter will be denoted omega in this talk. And so that's a traditional thing that we've learned in our first years at the university. But the question now is, what can we say about these distributions of a system when the system is away from equilibrium? That's actually a very old question that has been addressed by Leibowitz, McLennan, Zubarev, and many others. But the answer is usually very technical and unpractical. And here somehow the insight is to make use of the macroscopic limit to get something much simpler. And I will try to convince you that if one focuses on non-equilibrium steady states, these rate function characterizing the probability distribution in the large omega limit can be related to actually the entropy production of the macroscopic relaxation dynamics, because in the large omega limit, the dynamics become deterministic. The macroscopic dynamic becomes deterministic, and it's, I think, quite remarkable that this rate function characterizing the fluctuations of a steady state can be expressed in terms of the dissipation along relaxing trajectory of the deterministic dynamics. And in the passing, the example that we will look at also displays a non-equilibrium phase transition to show that these type of approaches can be used to characterize the emergence of phase transition, new behavior, symmetry breaking also away from equilibrium. This is work with Nahuel Freitas and Gian Maria Falasco. And if time permits, I will also say a few words about a different type of phase transition that we found, which occurs when a system is quenched and then relaxes to equilibrium. And this is really a dynamical phase transition, because this is now the time-dependent probability distribution with the time-dependent rate function, and we will see that it displays a kink that appears at a critical time after the quench. And I hope to have time to say a few words about that. So I will be quick here because I assume the audience is familiar with the basics of stochastic thermodynamics. So I will use the master equation formulation with this notation where the states are labeled by this vector n, and this delta vector here denotes the transitions caused by different processes. Rho, you can think of them as reaction. And so when a transition happens, these objects specify to which nu n prime the transition occurs. The local detail balance, which is crucial to make contact with thermodynamics, states that the log ratio of the forward and backward rate between two transitions is related to the change in the energy or free energy. You see, in case the state has an internal entropy, I also put the entropy here. To make it easier, I will assume isothermal system, but it's not needed. Everything can be generalized, but then I need to play with Massieu potential, and people are typically less familiar with that. So I will stick to isothermal system and work with free energies. So that's the conservative part of the transition. And then the non-conservative part that cannot be written as a difference between two states, that the non-conservative work that also contribute appears in this local detail balance. With that, one can write a first law, balance of energy, and identify work and heat, and a second law where we have the famous entropy production that is always non-negative, measuring the break of detail balance in the system, and that is equal to the change in not only the Shannon entropy, because I have an internal entropy, so the entropy is made of the average of the internal entropy and the Shannon term, and the heat divided by the temperature of the reservoir. One can also introduce the non-equilibrium free energy and rewrite the second law as such. So let's move on. Now I go back to a result that I obtained a long time ago, and that is quite cute, but I think had very little practical implication, and I want to mention it because it's going to be crucial to derive the results that I want to show. So one can do an alternative splitting of the entropy production in terms of two non-negative contribution, one that one calls the adiabatic contribution, the other one the non-adiabatic one. And the idea is simply that these currents, which are given by the rates times the actual probability, are transformed now in currents with the steady state probability. So you see here I have now the steady state probability in this term, the adiabatic one, and as a result in the non-adiabatic one I need to compensate for having replaced P by P steady state, and so this is what I need to make sure that the sum is still the entropy production. And the nice feature is that these two contributions are separately positive. This one measures the breaks of detail balance in the steady state. So if the steady state doesn't break detail balance, this contribution will be 0. And this one measures the displacement, can be written more explicitly even as, in absence of time-dependent driving, as the total derivative of a relative entropy measuring the displacement between the actual probability distribution and the steady state one. So this is also for isothermal system. The adiabatic one has been called the housekeeping heat divided by temperature. So I wanted to mention that because I will come back to this split later on. Okay, so now let's take the macroscopic limit. I will first do it formally, but then show you that there are many systems that have these features. So I will assume that we have an extensive scale parameter. It can be the volume or the size of the capacitance in an electronic circuit. And I introduce the variable density, which is the n divided by this scale factor. And I assume that the transition rate are extensive in omega. And so these small omega now become my intensive rates because I divided the extensive one by omega. And the free energy also need to be extensive, the free energy of the states. So same thing here, small phi will denote the intensive free energy of the state. And if these conditions are satisfied, one can actually show that the probability distribution satisfies a large deviation principle. So this notation, I think most of you are familiar with. It simply means that I'm disregarding everything that is not exponential in omega. So everything sub-exponential is dropped. And if I replace now this large deviation ansatz in the master equation, I obtain an equation for the dynamics of the rate function itself. That is going to be the object that we're going to look at. Now, an important further property of this is that the minimum of the rate function, which corresponds to the most likely probability distribution, because the minimum of I gives me the maximum of P, corresponds to the deterministic dynamics. One can actually show from this equation that the minimum satisfies this deterministic dynamics, where X now is the deterministic trajectory, and typically U is a nonlinear dynamic. So the macroscopic dynamics will typically be nonlinear and expressed in terms of these intensive rates. So in chemistry, this would be the rate. This will be the kinetic rate laws, mass action laws that we learned in high school. So there are, as I was alluding to, there are many systems that display such extensive limits. It's absolutely not something special. And I would even argue that this is the way that one has to scale the theory to recover also the fact that at equilibrium in a macroscopic system, we know that extensivity is present. So the natural way to generalize this is to consider this scaling of the dynamics, to have a non-equilibrium macroscopic theory. And classes of systems can be chemical reaction networks, where one looks here at the number of species of each type of molecule, number of molecule E, E star, etc. Or it can be an electronic circuit when one looks at the number of electrons on a conductor. The example I'm going to use is taken from circuits. Or Potts model, where we have different interacting units and one looks at the number of units in a given state. So the Ising model is a special case, but it can be generalized to many state units, reaction diffusion, and many others. Okay, now at steady state, this is simply the dynamical equation I had before for I. So at steady state, the probability distribution doesn't depend on time, so this derivative becomes 0, and we need to basically solve this equation to get the steady state rate function. What is known is that this rate function is a Lyapunov function of the deterministic dynamics. It means that if you evaluate this function along a deterministic trajectory, so a solution of, a solution of this deterministic equation, it always decreases. And we also know that for detailed balance systems, this rate function is given by the free energy, as we saw at the very beginning. But beyond that, I will also show you how to recover this property of the Lyapunov function. But so these were the known things, but now the new result will be the following. The entropy production of the deterministic dynamics is always greater or equal to the decrease of the rate function along that deterministic dynamics. So the entropy production along the deterministic dynamics depends on the path, and this is a difference between the rate function at the beginning and at the end of the path. So this is the illustration here. This is the path, and this is the 2 points where we evaluate the rate function. So it's remarkable because you see a property of the deterministic dynamics, and which is related to a property that defines fluctuations in a non-equilibrium steady state, as I remind here. Now, furthermore, we can show that at equilibrium, close to equilibrium, sorry, the bound is saturated. And so in that case, this difference in rate function is really equal to the entropy production. So briefly, how to show that. So when omega becomes big, this probability becomes very peaked around the deterministic trajectory. At this point, because it's a minimum, the gradient of I is 0. Because of normalization of the probability at that minimum, I itself is 0. And so in terms of the thermodynamic, what does it mean? It means that the Shannon entropy will be 0 because it's an average of log p. If you replace log p by this exponential, you get an average of the rate function. As we said, p is very peaked around x, the deterministic value. So we get I in x, and this is essentially 0. This means that the entropy production, which is the Shannon entropy, including the internal entropy. So what is, as we just said, the Shannon drops. So what is left is only the expectation value of the internal entropy of the states and the heat flow that become, when scaled divided by omega, the intensive quantity corresponding to the deterministic dynamics, the entropy production along the trajectory, the internal entropy along the trajectory, and the heat along the trajectory. So that's, I would call this the traditional second law corresponding to the deterministic dynamics, where the Shannon contribution has completely dropped. Now, from the non-adiabatic entropy production that I mentioned before, one can get the following. Since the non-adiabatic entropy production is the derivative of this relative entropy, and the Shannon part of this relative entropy drops, we are left with an average of the steady state rate function, because P steady state satisfies the large deviation principle too. And this becomes the rate function at steady state along the deterministic trajectory. And therefore, the non-adiabatic entropy production that is always positive is minus the derivative of this rate function along the deterministic trajectory. And so that's a way using thermodynamics or using the adiabatic, non-adiabatic decomposition to prove that indeed ISS is a Lyapunov function. But this was known. Now the new thing is to realize that the adiabatic, non-adiabatic decomposition tells us that the adiabatic contribution is the total entropy production minus the adiabatic one. And when scaled by the size, we get now that the entropy production rate along the deterministic trajectory plus the change in steady state rate function is always greater or equal to 0. And so if we integrate this result, we get the result that I showed you before here. The first law is very basic, is as it is. So the change in energy is split into heat and work. Now, at steady state, so as I said, the bound is saturated when we are close to equilibrium. I will not go into the detail here, but just give you the idea. So this is the equation defining the steady state rate function together with the local detail balance condition, knowing that at equilibrium, so when there's no non-conservative work driving the system, we know, as we said, that the rate function is given by the free energy. And so now we basically define G to be the difference between the rate function and the free energy, assuming that this departure from equilibrium will be small. And so one basically plugs this in this equation using the local detail balance and develops things to first order in G and W. And one gets the following equation, where the drift now is the drift corresponding to the deterministic dynamics with unperturbed rate, meaning rates which are not driven. And same thing for the work. The work is now evaluated using the dynamics, the undriven dynamics, so the equilibrium dynamics. So the flavor is the same as what we know from traditional linear response theory, except that we are working now at the level of the rate function instead of the probability itself. And by integrating these results, one can actually get that the change in this rate function along the deterministic trajectory is the entropy production calculated with the unperturbed rates, which can be written as the difference in free energy along the trajectory, plus this work evaluated along the unperturbed dynamics. So this is the unperturbed dynamics given here. So we also recovered the fact that in absence of work, so when we are really in a detail balance scenario, relaxing to equilibrium, not close to equilibrium, but to equilibrium, we recovered that the difference in rate function is only the difference in free energy. This is a powerful tool, and I will not show you the numerical evidence for that. I will simply give you the ingredient for saying that this is a more powerful linear response theory than the traditional one, because one works at the level of the rate function, which is the argument of the exponential, and one expands the argument of the exponential, which is better than expanding the probability distribution itself. So one exploits the macroscopic limit to go beyond traditional linear response. Now, let's look at an application to illustrate a bit the results that I mentioned. So this is a CMOS memory or CMOS bit. So briefly, it's made out of two inverters. That's a traditional trick, to use the output of one inverter and feed it as the input of another one to create a bistable state. And the state space is given by the number of electrons, which corresponds to the potential, on this conductor here and on this conductor here. So these are the 2 degrees of freedom, and these are the powering voltages. The system is driven out of equilibrium by these that you can think of set fixed potential, like chemostating in chemistry, but in the context of electronics, there's a battery, for instance, setting the potential of these conductors here. And so if one looks at the distribution in phase space, where V1 and V2 again are the number of electrons proportional to the number of electrons of each of these 2 conductors, away from equilibrium one gets this bistability. And if one looks along the x direction, which is this one, and one starts from close to equilibrium and one increases the drive, one sees that one goes from a single minima, which would be here in the middle. So it's the system is not working as a memory when it is not powered, but as the power increases, there's a transition to a bistable distribution. So this is a non-equilibrium phase transition because we are out of equilibrium. And we plotted here, I didn't do it, Noel did it. We plotted the linear response prediction and compared it to the actual result. And you see that even relatively far from equilibrium, we still have a very good agreement between the rate function and the prediction from linear response. And let me also emphasize that we are actually here at the omega factor that is only 10. So when I was talking about the macroscopic limit, this is kind of the lesson that of all these works in the last year, is that the macroscopic limit and large deviation theory, although formally is a theory for very large omega, it works remarkably well already at very small omega. Now let's see how the emergent second law works to bound the rate function. So it can be used in 2 different ways. One is to lower bound the rate function. In this case, one actually starts from this point and evaluates then the entropy production along a deterministic trajectory. And same thing here. You see the trajectory are depicted here. So this one corresponds to a trajectory starting here and going to the minima. The other one starting here and going to the minimum. And as the bound predicts, we are the actual rate function is above these lower bound. Notice also that at zero, the bound becomes worse and worse, not at zero, sorry, at the minimum, because the system, the entropy production keeps increasing because it's a non-equilibrium steady state. And that's why very close to the, to the minimum, here we have this effect here. But we can also use this bound in the opposite direction, because one may argue that it's not easy to find the initial point here to start with. So what we did here is, assuming that close to the minima, we have very good sampling power. So sigma here is the standard deviation. So one could use a Gillespie algorithm to actually get the rate function in this region quite easily. And then one back propagates the deterministic trajectory. And by doing that, one would then upper bound the rate function. And on one side, it works very well, on the other one, a bit less. But this is already pretty good. And so this also confirms numerically the result that I was showing you. I forgot to mention that in this electronic system, there's no internal entropy. So the entropy production is exclusively given by the heat released. So it's one only needs the heat released, the Joule heating here along the deterministic trajectory to make prediction or about the rate function to bound it. Now, let me show you that we can get actually much better bound, because until now, I always referred to the physical entropy production, but the non-adiabatic adiabatic decomposition is actually a mathematical statement that can be expressed in terms of a mathematical entropy production that doesn't care about the fact that there are many processes connecting pairs of states, and so one can lump them all together. The dynamics will not change, and the coarse grain entropy production corresponding to that dynamics, where all the rates have been lumped, is a lower bound. But in this case, it's good to be a lower bound, because that allows us to actually get a better bound for our rate function. And in this model, it works remarkably well. In that case, you see the agreement is almost perfect. So this is essentially an equality. These are, again, the two trajectory along the direction x, but there's also this third trajectory here to show you that it's not only true along x. And finally, we should still explore how far we can push this as a method to calculate rate function. But Noel has done a very simple, has taken a very simple grid here. It's not even a grid, it's only a square of initial condition that he runs and lets the deterministic trajectory go and evaluates the entropy production along that. And from that reconstructs the entire rate function. And what we get is matches extremely well with the actual rate function. Of course, here you cannot see it quantitatively, but I can assure you that it works remarkably well. How system specific this is an open question. And the ideal scenario is the scenario where the coarse grain entropy production would correspond to a detail balanced dynamics. But that system here is not detail balanced, despite the fact that it looks like it, because the agreement is so good. So that is something we checked. Okay, so I will take a few more minutes simply to give you a taste, a flavor of this last result, which is the dynamical phase transition in an Ising model or Curie-Weiss model. I will go quickly because I assume most of you are familiar with the Ising model. So we have
you are at 30 minutes, just so you know.
Yeah, we have interacting spins. This is an interacting term. an entropic contribution and an external magnetic field. The rates satisfy local detail balance. We have a master equation describing this. And the rates have the property that they are invariant when the magnetization is switched to minus the magnetization. This system has a phase transition. So if we look at the rate function of the equilibrium probability distribution, this is the free energy. It's we can think of it as a potential. And the way to characterize the phase transition is by plotting these potential. At high temperature, there's a single minima, but as one gets close to a critical temperature, at zero magnetic field, there's a continuous phase transition. And one can also turn on the magnetic field, but we will focus on the situation where the magnetic field is off. This is the phase diagram, and let's focus on the zero magnetic field situation. So this corresponds to the hot region, this corresponds to the cold region, and what we will consider is a quench where we start from the region of coexistence, where we have two minima, and we are at equilibrium, and we do a sudden quench of the temperature and let the system relax to the new equilibrium, which will correspond to this rate function here. And we will look at what happens in between, okay? So this is the standard bifurcation diagram of the magnetization as a function of the temperature, where the magnetization is zero and then becomes, that solution becomes unstable, and we have the two stable solution appearing. Now, to do that, I skipped the technical detail, but essentially it's solving the equation for the rate function that I was showing you, realizing that this is basically an Hamilton-Jacobi equation, and the solution to that problem are not unique, and this is what will cause the phase transition, but one needs to pick the one minimizing the rate function, because that's the one giving rise to the most probable behavior. And this is the main plot I wanted to show you. So if we start from this equilibrium state here, when the system has two stable fixed point, one starts the quench. And now as we move along these curves, the time is evolving. So at the end, we will end up in the final equilibrium state. But notice that as time evolves, at the beginning, at short time, the curve, the rate function is still smooth, but at a critical time, there's a kink appearing in the rate function. And that kink then goes down, but doesn't disappear and remains there over long times. I will just give you a flavor of what is happening. At the level of these Hamiltonian trajectories solving the Hamilton-Jacobi problem. When we are at times that are before the critical time, the most likely trajectory giving rise to a given magnetization are the ones starting from the initial very unlikely points and remaining there until time t. After the critical point, the new set of trajectory that become the most likely one are the one that start in the bottom of the wells, and there are two of them because we are bistable, and over time move to m equals 0. And that's the mechanism creating this kink in the rate function, and one can really map the equilibrium diagram, phase diagram, into an analog diagram for time and magnetization, but this I will skip because I don't have the time. So let me conclude. I showed you that the emergent second law relates macroscopic density fluctuation in a non-equilibrium steady state to the dissipation along macroscopic relaxation dynamics. I think it feels like giving a new meaning to the notion of the relation between dissipation and fluctuation. It's not, of course, a standard fluctuation and dissipation relation. It's much more than that because we are talking about the full rate function. But I like to think of it in that way. It can be used to compute rate functions. And I also briefly showed you that we can use this method to calculate rate function to identify a dynamical phase transition which manifests themselves as a kink in the rate function after a quench. Thank you very much for your attention.